Okay, let's do some exercise to find velocity profile, shear stress profile, and relating the variables. The system in this particular problem is a flow of water through a thin slits. Slits on the left hand side, this slit is stationary, so it's stationary. That means it doesn't move. On the other hand, this wall is moving upward with velocity v. In between, right here, we have water. So if the velocity v here is very slow, water is supposed to go down. So therefore, normally, we take one direction of the axis going along the flow. So that's why I assign x-axis to go down together with water. The rest of the coordinate should be y and z according to the rectangular coordinate. On the side view, we have this picture. If we assume that the system that we consider is rather short, so that acceleration of water can be negligible, then we can neglect the velocity as a function of z direction at all. Also, if we take the dimension w to be very large, we can neglect all the end effects on the left and on the front and on the side, this and that completely. The details of the question asking for the shear stress profile and velocity profile, both of them supposed to be found using shear momentum balance. So let us work on these two problems first. This is the enlargement of the picture. Now, according to this picture, it is obvious for us that velocity component Vz is supposed to be 0. There's no way that water is flowing perpendicular to the screen. Also, it should be found that Vy is equal to 0. There's no flow in y direction. Otherwise, once the water hits the wall, there's no way it can go through. And it is obvious that Vx is not 0. So we need to analyze whether Vx is a function of which variables. So we have x, y, and z. It is definitely that Vx is a function of y. Why? Because along this direction, you can see that this particular point, velocity is supposed to be 0 under no slip condition. But in between, velocity is not 0. So velocity Vx is changing with respect to y for sure. On the other hand, as we discussed, we neglect the acceleration, so therefore Vx along z direction is supposed to be constant. We can neglect function of z over here. We neglect acceleration, so we neglect function of x over here. I'm sorry. But for z direction, since we neglect the end effects on both ends, so we can say that Vx is not function of z. Once we analyze something like this, we always say that whenever we have velocity as function of this variable, in this case y, the shell is supposed to be thin in this direction. So my shell is supposed to have the thickness of delta y. In x direction, it's supposed to be full size because it is not function of x. Full size in x direction has dimension of L, and full size in z direction has dimension of W. So if I draw a shell in the picture with the length of L, width of W, and the thickness of delta Y, I should get this picture. So this is delta Y, and full length of Y of W and L. Alright? So, if we determine velocity component already, then we know that now we have Vx only. Vx supposed to be responsible for momentum in x direction or x momentum. So we are going to ignore y momentum because Vy is 0 and ignore z momentum because Vz is 0. X momentum can be transferred in 3 directions, represented by Vxx, Vyx, and Vzx. Okay, this is Vxx supposed to be x momentum, transfer in x direction. Vyx is x momentum, transfer in y direction. And same thing apply for Vcx. In detail, Vxx is equal to tau xx plus pressure. Whenever both subscripts are the same, we need to add pressure in x direction plus bulk transport rho Vx Vx. Vyx is supposed to be equal to tau Yx plus rho Vy Vx. And Vzx is equal to tau Cx plus rho Vz Vx. If we draw a shell again, this is z direction, x direction, y direction. Now the direction of the transfer goes along each direction. So for Vxx, it is transferring in x direction. So it's go this way in x direction. So you have Vxx going in and out in x direction. The double arrows represents the direction of the transfer of the flux. For Vyx, it is transferring in y direction, so it's go from behind here and go up front. This is Vyx. And Vzx going in z direction, that's going from behind and going out up front of here. Alright? Now we have to determine each component whether it's 0 or not. So the easiest way, easiest one that we can start, that should be the bulk transport. We know that Vz is 0, Vy is 0, so therefore this term is 0, this term is 0. Vx is not 0 at all, so we need to keep this term. This term must be kept. Alright? Regarding the term tau, we need Newton's law. So let's bring up Newton's law of viscosity. This is Newton's law of viscosity in rectangular coordinate. Let us cut it out. Go back to our problem and press it here. Now, since our liquid is incompressible, so according to what we discussed in chapter 3, for incompressible fluid, del dot V is supposed to be 0. Or I can prove it to you here. Down here, this is definition of del dot V. Now, Vy is 0, Vz is 0, Vx is a function of y only, so Vx is not function of x. This term must be 0, leading to this del term to be 0. So this term is 0, 0 over here. So we don't have to worry about viscosity in these three terms. For each shear stress, Vx is not function of x, so the first term here is supposed to be dropped, leading to be 0 for tau xx. Vy is 0, so tau yy is supposed to be 0 as well. Vz is 0, tau zz is 0. Vy here is 0, but Vx, in our case, is a function of y. So this term is not 0. Vz for here is 0. Vy is 0. This term is supposed to be 0. Vx is not function of z, so the whole term here is supposed to be 0, and Vz itself is 0. So this shear stress is supposed to be 0. Alright? So if you notice, we have two terms. One is related to y momentum, and this term is related to x momentum. Although by the magnification, this term is not 0, but we don't have to worry about this term at all in our problem, because right now we only have x momentum. So if I go back here, now we have a conclusion that tau xx is 0. Tau yx is not 0, this term must be kept, and tau zx is 0. So we don't have to worry about phi zx at all. So this term is supposed to be not related to our problem. Alright, so we need to take a balance between these two terms. Okay, so let us clear this out of the way. Now, it's time to do the momentum balance. To make it easier, let us focus at each plane. Now, since this term is already gone, so we don't have to worry about this area at all. In other words, for xy plane, we got 0 flux going in and out. For xz plane, which is this area, this is xz plane, the in term supposed to be flux in this direction, perpendicular to this highlight area. The in term supposed to be tau yx, but we know that tau yx is essentially, right here, tau yx is essentially, phi yx is essentially tau yx. So in term supposed to be tau yx going in. It's going in at y, right here, going in at wider position of y, multiplied by the area perpendicular to the flux, and the highlight area is W times L. This is W, and the length here is L. So the highlight area is WL. For output, it's supposed to be the same thing, except the location is y plus delta y multiplied by the same area, right? Then YZ plane. For YZ plane, it's a plane on the top here, and the flux going in and out in this highlight area supposed to be phi xx, which is equal to pressure multiplied by convective transport. So my in term is supposed to be pressure of x at x equal to 0, which is located on the top here, plus rho Vx at the same position, multiplied by the area perpendicular to it, and this highlight area is supposed to be W times delta y. W is the length, the width here is delta y, so W delta y. Same thing for output term, supposed to be pressure at the bottom, x equal to L, plus rho Vx at the bottom times the same area. Alright. Last term in the momentum balance is supposed to be force. And force relating to the flow is gravity force, force relating to the weight. Weight can be calculated by mass times g, and mass is basically volume times density. Volume that we are talking about is supposed to be volume of the shell. Shell has a volume of WL times thickness of delta y. This is volume times rho to convert into mass of the shell times g. That's the weight or the force. And you can notice from the picture that g is going down. So along with the x-axis, in this case, g is a positive sign. Now we have all the items ready to put in the balance. So let's start with these two terms. WL tau yx at y minus tau yx at y plus delta y plus these two terms, W delta y pressure, let me call this pressure P0, subtract pressure PL, plus rho Vx, I'm going to put it square over here because Vx here and Vx here, both of them are scalar. So scalar multiplied by scalar, I can get square term. So Vx squared at x equal to 0 subtracted by rho Vx squared at x equal to L. Plus force term, which is WL delta y rho g equal to 0. Alright, this is our shear balance. Now, we know that this pressure, these two pressure are not the same. Pressure underneath is supposed to be a little bit higher because of the weight on top of it, but it's not necessary so. But definitely these two are not always equal, so we have to keep it. On the other hand, Vx at x equal to 0 and Vx at x equal to L supposed to be equal, because we stated earlier that Vx is not a function of x. So therefore, these terms cancel out. Alright? So if I divide the whole term by WL, so WL here will be gone. W will be gone here, and we will have L as denominator. If I divide delta y as well, so we end up with tau y x at y minus tau y x at y plus delta y divided by delta y itself, plus P0 subtracted by PL divided by L. Delta y here will be gone. And then the fourth term would only have rho g equal to 0. After taking limit, if you take limit delta y approaching 0, this whole term turns to be differential. So what you have would be negative d tau yx by dy plus P0 minus PL over L plus rho g equal to 0. And then, just like what we did in the problems earlier, the pressure term here, here, and the gravity term can be combined. If we define modified pressure at I equal to pressure at that position minus rho times g and the position itself. So if you extend this denominator over here, you should have L over here, and PL and this term can be combined according to the definition. Here supposed to be modified pressure 0 subtracted by modified pressure L divided by L, and then I can take this to this part, right? By integration, the right hand side, you can write it first. After integration, you have tau x, tau yx equal to modified pressure 0 minus modified pressure L over L times y, if you integrate it by y, added by integration constant C1. And then we can go ahead and replace the tau into velocity, because at this point we don't have boundary condition to find C1. At this point we don't. So we will go ahead and replace tau yx using Newton's law that we defined earlier, that tau yx equal to minus mu dvx by dy. So if I plug this here, I'm going to get dvx by dy equal to minus, turn to the right hand side, pressure difference over mu L. I take mu as the denominator to the right hand side, y over here, and then plus from here turns to be minus C1 over mu. And then you can take integration, Vx, integrated with respect to y. This up front remains the same. You have y squared over 2, just put 2 over here, minus C1 over mu times y, plus another integration constant C2. Now we have two unknowns, C1 and C2. Therefore, we need two boundary conditions. So, the first boundary condition, we know that if you go back to the picture here, at y equal to 0, which is this position, at y equal to 0, velocity Vx is 0 because the wall, this particular wall, is stationary. On the other hand, this wall at y equal to delta, which is the thickness of the gap, Vx is equal to the velocity of the wall itself. In this case, we have to be v. But keep in mind that velocity v is going upward. This is velocity v, but our x-axis is going downward. So we need to put minus sign over here. So we have two boundary conditions. First boundary, at y equal to 0, Vx is equal to 0. So 0 on the left, y equal to 0, that means first term is 0, second term is 0, plus C2. So you get C2 equal to 0. Second boundary, at y equal to delta, Vx is equal to minus v, as we discussed. So minus v on the left equal to minus pressure difference over 2 mu L. Then we put y to be delta square, subtracted by C1 over mu times delta, and C2 is already 0 according to here, so we put C2 equal to 0 over here. Then we can solve for C1. But since in the velocity profile we always have C1 over mu, we don't have to find C1 by itself. All I have to do is just to find C1 over mu. So C1 over mu, just move the whole term here. Put this term to the left hand side and rearrange the equation. I get C1 over mu to be pressure difference over 2 mu L, and 1 delta here and 1 delta there cancel out, and you have V over delta, because we need this term to go to the right hand side. So once you get C1, C2, then you can plug it back to the original equation. So Vx, according to this part, should equal to minus PL P0 and PL over 2 mu L y squared minus C1 over mu. And you have minus here and minus over there. That turns to be plus. P0 PL over 2 mu L. This is part of the C1 over mu delta times y. Y is here. And then subtracted by V over delta. Okay? You need to make sure that this is minus, so this plus turns to be minus eventually. Alright, the rest is supposed to be cleaning up the equation. So if we take a common term over 2 mu L, just take this term up front, then you have delta times y subtracted by y squared from the first term subtracted by V over delta. Oh, you have to put y over here as well. So it's supposed to be y over here. So I have V y over delta. Alright. So this should be your velocity profile. Okay. So if you want to find shear stress profile, you can either calculate it back from Newton's law, tau yx equals to minus mu dvx by dy. Just take differential of this equation. But it's not necessary because we got this part already. So if you just take C1 according to what we found earlier, plug it in here, then you can find shear stress. And the answer for tau yx, that should be P0 minus PL over L that should be your shear stress profile. Alright? Now, you may be wondering, do we have to do shear balance every time? If you prefer to use equation of continuity and equation of motion, you should be able to get the same answer. So let me show you how to get the answer. To use equation of change, there are two equations at first. The first equation is supposed to be equation of continuity. Let us call it up. This is table for equation of continuity. Just take Cartesian coordinate, copy, Put it here. Then we can eliminate terms. Steady state, this term is supposed to be 0, and also you can say that your fluid is incompressible. Density does not change with respect to time. Vx is not 0, Vy is 0, Vz is 0. So at the end, density, which is constant, this part can be taken out in front of the differential. dVx by dx equal to 0. In other words, Vx is not function of x. Alright? Second equation supposed to be equation of motion. But if we take assumption of incompressible fluid and Newtonian fluid at the same time, you can use Navier-Stokes equation. Let us call up of Navier-Stokes equation. This is Navier-Stokes equation for Cartesian coordinate. Let us copy. Alright. This is x direction, y direction, z direction, or x momentum, y momentum, and z momentum. In x momentum, steady state term, the whole term turns to be 0. Vx is not function of x according to what we found here. Vx is a function of y, but Vy is 0, Vz is 0. We have pressure gradient in x direction, so this term is supposed to be kept. This term, on the other hand, is 0. Vx is function of y, this term must be kept. Vx is not function of z, this term is 0, and we have gravity in x direction. So, if you go briefly through y momentum and z momentum, you see that a lot of terms will be removed. For instance, all the Vy should be 0. And there's no gravity in y direction, therefore what you have here is supposed to be Py, or P in y direction. P is not function of y. That's all we have. So from y, you end up with dP by dy equal to 0, or P is not function of y. For z momentum, Vz is 0. These terms are eliminated. You don't have gravity in z direction. In the same manner, you have dP by dz equal to 0, or pressure is not function of z either. Alright? Then that might be useful for us should be equation from x momentum. So from x momentum, the left hand side is 0. Right hand side you have dP by dx plus mu del square Vx by y square plus rho g. In this case, g and gx are the same. To make it a little bit more easier, you should see that right now pressure is a function of x only because it's not function of y. It's not function of z. So in this case, I should be able to write pressure in terms of total differentiation. And earlier, we already determined that Vx is a function of y only. So we can change partial differentiation to total differentiation as well. Alright? Then, if I take pressure term and gravity term to the left hand side, I will get dP by dx minus rho g equal to mu d squared Vx by dy squared. And you should realize term on the left hand side are function of x only. Pressure is function of x, rho g a constant. While term on the right are function of y only. These two terms, this equation is always correct, but one on the left is a function of x, one on the right is a function of y. The only possible answer for equality is that both are constant. Okay? So, if both sides are constant, then I can split the equation into each half. Start with the left hand side equal to C0. If I take rho g to the right hand side and integrate, I should get pressure equal to C0 times x, because I integrate with respect to x, plus rho gx plus another constant C1. Then we have two unknowns, Z0 and C1. We need two boundary conditions regarding pressure, which we do have. So the first boundary condition, as x equal to 0, pressure is P0. So if you put x equal to 0, left hand side is P0, right hand side first term is 0, second term is 0, and then you have C1. So C1 is basically P0. For second boundary, at x equal to L, P is equal to PL. So plug it in. C0 times L plus rho GL plus C1, which is P0. I take this in here. So in this case, you can solve for C0. C0 supposed to be PL minus P0 minus rho GL over L. And again, we can combine PL and rho GL using modified pressure, definition of modified pressure, and eventually you get modified pressure PL subtracted by modified pressure P0 over L for C0. Alright? So for the second half of the equation, you have mu d squared Vx by dy squared equal to C0, which is taken to be known. If you integrate it once, you get dVx by dy equal to Z0 over mu, taking mu to the right hand side. Integrate with respect to y, you get y over here, plus another integration constant C2. But we don't have any boundary condition regarding dV by dy at this point, so we just keep going on integration, and we get Vx equal to C2 y squared over 2 mu plus c2y plus another constant c3. Now we need two boundary conditions for two variables c2 and c3. Keep in mind that c0 is already known. So what should be the boundary condition? Same as what we did. At y equal to 0, Vx is 0. So taking Vx to be 0, y equal to 0, first term is 0, second term is 0, then you have c3. So therefore c3 over here is 0. Second boundary, at y equal to delta, Vx is equal to minus v. So plug it in, minus v equal to z0, y equal to delta square over 2 mu plus c2 times delta. And c3 is gone because it was proven to be 0. So in this case, you can have c2 over equal to minus z0 delta, because 1 delta over here would cancel out with 2 over there, and then minus v over delta. So if you plug c2 back here, you eventually get Vx equal to z0 y squared over 2 mu minus c2, which is z0 delta over 2 mu times y here, minus v times y over delta. Then clean it up. Y squared minus delta y minus v y over delta. And then I would take z0 over here down there. So I have PL minus P0 over 2 mu L. Y squared minus delta y minus v y over delta. To make it the same as what we did previously with Shear balance, I'm going to take P0 first, and therefore I have to shuffle these two terms to get delta y subtracted by y squared. Then everything else should be the same. Alright? That's your velocity profile.